Hello. So if you've done any sort of insert applied maths by this point, you'd have likely come across these things known as difference equations. And these are equations which can model particularly discrete amounts of change. And you might have seen these two formulas crop up. So, particularly for a second order difference equation, if you solve what's called the characteristic of this equation and you get two distinct roots, then the general term, without having to find all the previous terms, is given by a constant times the first root to the power of n plus another constant times the second root to the power of n. And if they happen to equal, so in this case, if lambda 1 equals lambda 2 is some new root mu, then un is just c1 plus n amounts of c2 times that root to the power of n. Now, in pretty much all textbooks, they are just stated. There's no proof on why they are like that. You can sort of reverse engineer it. So if that is true, then you can work backwards and show that it definitely does work. You can do that. But what happens if you don't try this and you want a way of going about deriving these equations? Well, this is a video for you because I'm going to derive the two of them. Now, one warning before I actually do go ahead with this proof is that we're going to be employing techniques you'll find in the linear algebra course. So everything to do with essentially matrices and manipulating those matrices. And in particular, these four terms here, so eigenvectors, corresponding eigenvalues, the eigenbasis, diagonalization, and then for particularly the second one, we're going to get to a thing called the Jordan block. So you can Google the hell out of those topics if you really want to before resuming the rest of this video, or you can just sit back and watch this proof unfold. Now, I don't actually have the full proof entirely memorized, so I'm just taking it from little notes I have down here. So we'll start with the first case where we have two distinct real roots. We're not going to go into the complex roots or anything. So what I'm going to do is I'm going to define Vn, the vector, as a column vector with terms un plus 1 and un. However, through the use of matrix multiplication, we can rewrite any next term, so un plus 2 and un plus 1, as AB 1 0, a 2 by 2 matrix, times by un plus 1 times un. So if you were to multiply all these out, you'd get A times u1 plus B times un. So yeah, that's what it is. So un plus 2 is a un plus 1 plus b un. And then by definition, un plus 1 is just un plus 1. Now, you can keep going like this, and what you'll end up finding is that un plus some k, plus, well, k plus 2, un plus k plus 1, will end up giving you this matrix to the power of k times any previous terms. So what we can do generally is state that Vn plus 1 for some general amount n equals a Vn, where A is particularly this matrix AB 1 0. So if we go ahead and do this generally, but considering the first matrix, so u1 and u0, so we'll also define v0 as the column vector u1, u0. That means we can write Vn as a to the power of n times the vector v0, where again v0 is this column vector. Okay, so that's our first bit of information. So our second bit of information is to now consider looking for eigenvectors. So how we're going to do this is we're going to set the determinant of our matrix, take away lambda times the identity matrix of dimension 2. And we ideally want that to equal 0 for our particular eigenvectors. So that implies we want the determinant of A, so that's A take away lambda, B, 1, negative lambda, equaling 0. So the determinant is the difference between the product of each of the diagonals. So that's A take away lambda times negative lambda, take away B equals 0, which simplifies to lambda squared, take away A lambda, take away B equals 0. And this is, in fact, just the characteristic. Because if we rearrange un, we're going to get un plus 2, take away A lots of un plus 1, take away B lots of un equals to 0. So that's where that comes from. It's essentially skipping all the steps and arriving straight at this result. Okay, so we've gotten to that point. Now we need to define the roots. So we're going to define the roots as lambda 1 and lambda 2. Then we know that for these, that A minus, in particular, lambda 1 times the identity matrix I2 times of eigenvector x has to equal the 0 vector through the definition of an eigenvector. So that implies we're going to get A take away lambda 1, B, 1, negative lambda 1, times the column vector x1, x2, equaling the 0 vector, which is just a vector with 0's down the column. So if we do some comparison, we can say that A take away lambda 1, x1, plus B, x2, equals to 0. And then it's not too hard to see that you'll get x1 as the negative of B over A minus lambda 1 times x2. And what you'll end up finding is that this corresponding eigenvector for lambda 1 generally has the form of lambda 1, 1. And very similarly, v of lambda 2 will give you lambda 2 and 1. Okay. So those are the two eigenvectors. Now our next step is to consider a thing known as a diagonalization, which allows us to extrapolate a bunch of multiplications one after the other without having to carry out everything ourselves. So in diagonalizing this, we ideally want our matrix to be equal to E, D, E inverse, where E is the matrix of the corresponding eigenvectors, so it's lambda 1, 1, lambda 2, 1, and D refers to a diagonal matrix with the entries on the diagonal just being those corresponding eigenvalues. Now, a trick we can employ is that if we raise both sides to the power of n, we're going to get pairs of E and E inverse knocking each other out, bar the end terms. So a to the n is E times D to the n times E inverse. So from before, we know that Vn is a to the n times V0, which we can now equally say that that's ED, E inverse V0. But we already know what V0 is. V0 is just the column matrix un plus 1 un. Or sorry, u1 and u0. So not generally. It's u1, u0. So what we can say for this, because it's being multiplied by our corresponding eigenvectors, we're going to say that V0 is a linear combination, so C1 essentially of the eigenvectors. So lambda 1, 1 plus c2, lambda 2, 1. So just representing it as a linear combination of those eigenvectors. Now, when we equate these, when we essentially perform the addition of these, we're going to get c1 lambda 1 plus c2 lambda 2, and c1 plus c2 is the second entry. So we're going to do a little bit of comparing in zeros like that. So if we say that that's identically u1, u0, then u1 is c1 lambda 1 plus c2 lambda 2, and u0 is just c1 plus c2. So Vn is still a to the n v0, but we can now replace v0 with just, it'll be a to the n times c1 times the corresponding eigenvector plus c2 times, again, its corresponding eigenvector. Now, because each of these are eigenvectors, they will follow the property that a matrix times by the eigenvector, so the matrix multiplication, is the same as the scalar multiplication given that lambda is our particular eigenvector. So what we can say is that that must be true, and that will also equal lambda 1 to the n times lambda 1, 1. And similarly, so I shouldn't actually write implies there. Similarly, it follows on the same that a times v lambda 2 equals lambda 2 v lambda 2, which is lambda 2 to the n times lambda 2, 1. So now putting this back together, we're going to get Vn as c1 lambda 1 to the n times lambda 1, 1 plus c2 lambda 2 to the n lambda 2, 1, and these are all equal to un plus 1 and un. So if we just analyze the bottom entry, which are the ones with un, so un is equal to c1 lambda 1 to the n times 1, so c1 lambda 1 to the n plus c2 lambda 2 to the n, which is often rewritten as c1 times lambda 1 to the n plus c2 lambda 2 to the n, which is the result from up here, all the way back up there. Okay, so it's a bit of a long proof, and there's probably bits of it that might seem like entire black magic, but everything all links in. Okay. So that's the first case. The second case is what happens if we have a repeated root. So case 2 is if the root is just lambda equals to mu. Now I'm going to kind of skip ahead because it has the exact same start, in that we can arrive at Vn equals a to the n v0, where a is still ab on 0. And as well as that, the determinant of a take away, this time mu, times the two-dimensional identity matrix will still give us the results of lambda squared take away a lambda take away b being equal to 0. But if lambda equals mu is the only root, then by using the minus b formula we can come to the following conclusions. Firstly, mu is just a divided by 2. And secondly, if we note the discriminant, then we get the fact that a squared plus 4 lots of b equals to 0. Now, they might help us, so we might put a pin in there, we might come back to it later. So, one thing about these kinds of eigenvectors is that if there's only one of them, then it can't undergo any sort of diagonalization, because you're going to get 0 entries. If we go back to this D matrix, we're going to end up with a 0 here and 2 zeros here, which we can't realistically multiply. So what we're going to have to do is firstly state that a general eigenvector will be in the form of mu times 1, or mu1 as a column vector. And in particular, we're going to have to get another, or sorry, this is v1. I'm getting things confused. v1 is that, but that also means that a take away mu lots of I2 times some second vector v2 will give us back v1. And the following steps, because of a consequence of this, form what's known as a Jordan basis. Now this Jordan basis, made up of these vectors v1 and v2, is such that we get the following. We get P as a collection of v1 and v2, and a Jordan block matrix J to the power of n equals mu, 1, 0, and mu, where these are chosen such that A is equal to P times J, oh, I put the dot in the wrong spot, times P inverse, where A is still our matrix from before. So what we're going to get from a result that we saw before is, instead of diagonalization, we're going to get this. So Vn is still a to the n v0, but this time it's going to be P times j, this will be j to the n, sorry, times P inverse, all matrixly multiplied in the matrix form, times our vector v0. There's one other thing that we can do with the Jordan block, and we can express j to the n. Remember, j is mu1, 0, mu, but that's also equal to mu to the power of n times 1, n, 0, 1. That is just a standard result. Now, replacing j to the n with this new matrix, we still get v to the n as a to the n times v0 equals to the matrix P times mu to the n, 1, n, 0, 1, times P inverse lots of v0. So now what we're going to do is we'll do some sort of approximation, if you would. Is that we're going to guess, again, like before, that v0 can be made up of some linear combination of our vectors v1 and v2. So v1 and v2, remember v1 is that mu1 eigenvector, and v2 is the vector that solves a take away mu lots of the identity times whatever that vector is, giving us back v1. So what we can observe is that when you do a to the n times v1, you're going to get mu to the n times v1. That's again from the definition of the eigenvector. And similarly, a to the n times v2 is going to get you mu to the n times our vector v2, but n amounts of v1 for the amount of times that we multiply it. So through that, what we're going to get is Vn equals mu to the n times C1 V1 plus C2 times V2 plus n amounts of V1. Which, if we regroup this, get V to the n equals mu to the n times C1 plus n C2 times V1 plus C2 V2. And we know from the definition of how we assigned Vn is that this is equal to un plus 1 and un, that column vector. So again, we don't entirely know V1 and V2 explicitly, but that's because we don't really have to. One thing we can do is, for the fact that we have a freedom to choose V2, from the possible span of V1, then we can set V2 to give us 1, 0, and that will give V1 to be the vector mu1. And that actually does work. That is a result that you can prove. The reason for that is because we're trying to analyze all the second entries again. So this first entry we don't really need. So if we can eliminate any, or as much variance as we can to try to get that second entry, we're good. So by comparing the second entries, we get un equals mu to the n times C1 plus nC2 times by the V1 second entry, so I'll kind of put in like square brackets 2 for that second entry, plus, sorry, not beta, what am I doing? Plus C2 amounts of the second entry of V2. So that's the V2 second entry. But of course, the second entry of V1, that's just 1, and the second entry of V2 is 0. So it completely eliminates that term. And what we end up getting is our old favorite un as, rearranging this slightly, C1 plus nC2 times mu, that root, to the power of n. And that is how you use linear algebra to derive the two results from second order difference equations and the root theorems.